Let's now consider a typical application of the homogenization theory. In the picture you see the omega is this large set, and inside this set we have a composite material. For example, a composite material where you have fibers and matrix, some kind of glue which glue each of these fibers together. And for simplicity, we have chosen to consider a case where this, where the distributions of the fibers are periodic. This is, in fact, a typical example where it's rather difficult to use the finite element method or other numerical methods directly in order to find this solution. We see if we, for example, know the boundary conditions, and we know that we have the Poisson problem, for example, that we are considering a thermal problem, stationary heat conduction problem, which takes this form, and we have some internal source here which gives heat to the problem. So the problem of using solving this problem directly is that we get so many small elements here when we are discretizing, so it's very complicated to do it first, and secondly, the process of solving these systems of equations, which are incredibly large, will give us some problems. So an easier way to do this is to use homogenization theory and consider this material as some homogeneous material instead. And we are going to show you how this can be done. Here we have zoomed up the one period of this cell. So here is some conductivity in the fibers and another in the matrix. So the conductivity is in fact lambda 1, which is a constant in this area, and lambda 2 in the other area. Let's now show you how this can be solved, this problem, by using homogenization theory. In fact, it's possible to show that we can find the material properties of the corresponding homogeneous material, and that these the effective properties are different in the two directions, in the x direction and the y direction, or as we prefer to call it, the x1 direction and the x2 direction. And the solution of the original problem, which is the problem which we want to find the solution of, turns out to be very close to that of the more average problem, which this is, where these two parameters are given by some integral. And this is homogenization theory, which we will not go into, and we will not prove these results, but you have to just accept that these parameters are given, effective parameters are given by this formula, where I is either 1 or 2, and you see here we have some unknown solution U per is a periodic solution, in fact, and this solution, this quantity or this function is a solution to the following problem, which we will call the cell problem. The cell problem takes a usual form, is bilinear form, A of U per of and this phi equal to L of phi for all phi in no we are using a little bit different Sobolev space, namely the Sobolev space of periodic functions. And this bilinear form is exactly as before. However, this linear form, the functional L of phi, is a little bit different than we are used to. Here we have minus integral over this cell y of the conductivity lambda, which is piecewise defined as we showed you. And this vector E I is the unit vector in the ith direction. So solving this problem, we are able to find these parameters, and when we have found these parameters, we can insert it into this equation, and then the equation is much easier to solve because these parameters are constants. So now, instead of solving this more difficult problem, we replace this material with some homogeneous material instead, and it turns out to be very much easier to handle from a numerical point of view. So let us just mention that we have the following theorem, that the cell problem, which this is, has a unique solution within an arbitrary constant. That means that if we have two different solutions of the problem, then this difference will be a constant. We are going to prove this theorem, in fact, in the following videos.